Good afternoon, everybody. My name is Kevin Ross, and I am the founding chairman of Washington First Robotics. Welcome to Rookie Workshop number 2. Good question came up last week. So how do we go about designing robots for FRC, and what's the design process? So that is today's topic. We'll try and keep this under an hour. I think that we ought to be able to do that. So as far as our agenda for the day, let's take a look at, let's go ahead and take a look at the next slide here. There we go. So our topics for the day are thoughts about designing things with students, and then we'll talk a little bit about setting up a healthy environment for your team to be able to go through the design process. Then we'll actually talk about the design process, and then I'm going to give you a short technical tour of what it's like to design an FRC robot. So those are the basic topics for the day, and I hope that you will find this interesting. Let me start off by giving you some of my thoughts about designing with the kids. In general, this is something that very few people have experience with, which is in designing something, especially something new, using a large team. So when you have a lot of people in the room, or when you have a lot of people working on a common project, most people don't have very much experience doing that. And I do want to point out and acknowledge for the students that trying to get out their ideas and trying to work through something where they don't have direct experience with generates a great number of partial ideas, and those, expressing partial ideas when you're in a large group setting, there's a great deal of personal social risk there, and we need to acknowledge that, and acknowledge the fact that that some students will be timid, some will not, some will dominate the conversation, and others will become very quiet in the corner. So our goal throughout this process is to try and involve everybody at whatever level they feel comfortable with, and making sure that that they have an opportunity to participate. Now, expressing partially formed ideas is difficult enough for those of us who have been doing this for a long time. Communicating things clearly, especially when you haven't fully thought out an idea, takes some practice and takes a bit of time. So, part of this is allocating time to make sure that students have the opportunity to express themselves, to clarify themselves, and to sort of get their point across without falling into a few very common traps. So let's talk a little bit about the overall process for doing this. I think that it's really useful at the beginning with your entire group to think about this process. Think about the process that students are about to go through, and point out a few very important things. First is that active listening skills really need to be emphasized. Again, it's difficult to get your idea out correctly the first time, and if rather than shooting somebody down if you don't understand something, it's best to be a very active listener and engage in questions, and try and understand what it is the person is doing rather than immediately shooting them down. I think that's a really, really important skill to develop. And I think it's really important to acknowledge that the participants in this program will all have various levels of technical or management styles and capabilities. And so I think it's important for everybody to recognize that and to point it out very explicitly that some folks will be really good at this, and some people are going to need a little help, and it's up to the team to help everybody succeed in this process. I think agreeing that we're all on the same project sounds kind of strange, but I think it's really important that everybody realizes that the goal is for your team to do a great job on this project, and it's not a competition, local competition. Your team doesn't need to compete with itself. So keep that in mind as you're going through this, and being gracious and professional, which means trying not to belittle others, trying not to gain an upper hand or be overly aggressive is it works really well in a large group setting, and we really celebrate the teams that strive to make that happen. All right, and I think once you can establish a little set of rules of engagement for these design sessions, for the first few times, I would remind everybody, as you're getting started down a design discussion or brainstorming session, a quick reminder of the rules for at least a couple of first 3 or 4 times, whatever, is actually a very beneficial thing to do, just to remind everybody to be thoughtful of others. Okay. There are a bazillion ways of doing this. I'm a kind of a big favor of something that I always call the Make It Better game. So in the Make It Better game, what you want to do is set up some ground rules where every group has a facilitator, and that person is trying to remain neutral and open. They may contribute their own ideas, of course, but the reality is that person needs to be able to handle the idea that that they are there to help everybody else in the room get their ideas out into daylight so that everybody can see them. Okay, I think that everybody's ideas are solicited and recorded somehow. Put it up on the whiteboard or chalkboard or whatever it is that you've got. And I think a really important step of the Try to Make It Better game is comments about an idea should really come in the form of a suggested improvement, an alternative, or a question of clarification. So what that means is, rather than saying, oh man, that is a stupid idea, what you really need to do is suggest something better, or ask a clarifying question. Like, if you're trying to build a 2-wheeled robot, how do you plan, rather than saying, well, 2-wheeled robot is just a dumb idea, help people understand what it is that the thought process is behind that. Why isn't it a good idea? And you can always do that in the form of a question, such as, okay, interesting, a 2-wheeled robot, how are you going to make it stand up? How are you going to make it not fall over? And sort of ask questions or suggest improvements is just a great way of doing this. This Try to Make It Better game attempts to avoid the direct dismissal of any one particular idea. So you're always trying to take somebody's idea. You are on their side. They are on your side. Can you make it better? Can you suggest an alternate approach? Okay, and especially when you've got a room full of potentially aggressive folks, I think that having the facilitator be able to recognize when ideas are getting shot down in a too personal of a way, to sort of divert that and to calmly remind people that that isn't the way that we're operating. Okay, so you don't want to belittle somebody or reprimand somebody in public. That usually just shuts things down. But just a gentle reminder. Okay, we're remember the rules of the game are suggestions and improvements only. Okay. And so the facilitator oftentimes will need to remind the participants of the rules of this little game up front. I say give this process a try. Your team will work out its own little process on how to do things, but I think that this one works pretty good. What we're trying to do is set up an environment where the students are not raising their social shields to avoid ridicule, and I think that really makes a great team experience for everybody. All right. So in practical terms, there are some limits to the size of a group of people trying to all work on the same project. I really highly discourage you from trying to have a design session, a single design session with your entire team of 24 or 36 people or however big it is. Okay. I think the reality is, and from industries do this as well, really 5 to 7 people is about the most that you really want in on a design thing. 8 to 10 people is really the max. If you've got more than that, break it up into 2 smaller groups, because smaller teams with fewer people involved tend to do better and tend to generate more creative ideas, and everybody gets an opportunity to participate. If you get more than about 10 people, it's very difficult for some people to get a word in edgewise. Okay? And so multiple small teams are great. If you had a team of, say, 18 people in the room, break them up into 3 teams of 6 and say, okay, everybody, we're all working on the same problem today. Let's break up into groups and do some brainstorming among the 6 groups. And, towards the end of the day, we'll come together and each group will explain their ideas and you can use the same sort of make it better game then, but you've got a lot of people who have already participated and have got some ideas, okay? So I think presenting it to the entire group is actually an extremely good exercise there. All right. As far as setting up your team's environment, I found that a U-shaped room works best. If you've got a whiteboard or something, what you want to sort of avoid is standard classroom lecture seating. It always gives somebody too dominant of a position. And it also means that people in the front can't see the body language of the people in the back. So I think, if everybody can see each other while they're talking, I think that's really a great format. The circle format works as well, but inevitably you're probably going to need a whiteboard or a computer screen or something. So U-shaped or at least avoiding everybody sitting facing the exact same direction is a pretty effective way of doing it. All right, so those are sort of my ideas behind what sort of things that you should do when you're setting up your team environment. Now, one thing that's important before I jump into how to do the actual design process, part of this brainstorming and ideas session is communicating your ideas, and a lot of times we like to make little drawings. And drawings are awesome. However, a couple of pitfalls that you should watch out for. Scale and size are really very important. Oftentimes you'll see somebody draw an idea on the board that is might seem like a reasonable idea the way they drew it, but when you realize, if you're trying to pick up a 40-inch diameter ball with a robot that's only 28 inches wide, if you don't get the scale right, you sort of miss some very, very key features. So, putting a little bit of effort into the drawings you put up on the board and trying to keep things in relative scale is really very useful. Putting up a grid is great, or if you have yardsticks or something, have people draw it half scale or quarter scale or something. But try and communicate your ideas roughly to scale. Otherwise, it can be difficult to communicate your ideas. Okay. The other thing is, when you're drawing, remember that things are in 3 dimensions and everything has thickness. I've seen teams go way off the deep end and get very detailed in their drawings on the whiteboard, only to find out that when they looked at it if they went to design the thing, it turns out that all of the thicknesses didn't work out. So anyway, okay, probably enough about that. But I guess my key point to the new teams is, having a nice process for your team interacting with each other is actually very important, and it's a good thing to sort of get set up early. I went to find some slides about the design process, and I was amazed at how many variations of this thing there are. I just grabbed a handful of them. If you look on the internet, it's kind of crazy, and some of them are very lofty, like the one on the upper left here. Some are ridiculously too complex, like the one on the far right. I mean, who's going to follow that design process? You'd spend half a day just trying to figure that out. And you got a lot of stuff. They progress. They progress one step to the next. Others have incorporated backtracking stuff. All of these are fine, whatever. The reality is you just kind of got to pick one. But realize if you look through all of these, they all have something in common. Identify the problem, okay? Do research what it is that needs to be done, develop some solutions, select a solution, do some prototyping, test and evaluate, and then there's always the redesign issue. And you can see that here in the lower left. Identify the problem, figure out what the relevant information is, brainstorm, do those sorts of things, and you can see they keep backing up. And all of these do that. So The reality is that none of these flowcharts are actually terribly useful, other than you just need to realize that there is actually an order to some things and there's some structure to it. So if your team can come up with a structure for the design process that works for you, great. The reality, just pick one. So I just picked another one, right? This one had all the things I like to do on it, identify the problem, identify the criteria, those sorts of things. It's kind of good to throw this picture up so everybody realizes what you're going through, but I wouldn't get terribly inattentive about following each line individually. So how do I take something like this sort of really broad, generalized design process and sort of apply it to doing an FRC project? Well, it turns out that if as far as identifying what the problem is, the reality is you need to read and understand the game rules. That's step one. You can. It's fun to theorize and think about mechanisms, and please do that. Let people think about stuff. But the reality is, before you start getting serious about any sort of design work, you really have to understand what it is that you're building. And to do that, what you really need to start out with, what is it that how does the game play? What is it about how your team is going to play that game, and in a way that makes sense, okay? So before you take too much of the brainstorming on robot ideas seriously, I'd really encourage you to think about how is the game played, how are the scores, how do you score points, and those sorts of things, okay? I'm going to go through each one of these in a little bit of detail, but you can see it's, it's sort of identify what the problem is, brainstorm, prototype, come up with a strategy that you really do want to build your robot, test your robot, and practice, right? We'll go through each one of these a little bit here. So for example, reading and understanding the game rules. Be sure you understand how to score. I think that's really important. And FRC games have a lot of nuance to them. The exact details of how to score can get very complex, and they can be, there are usually multiple levels of scoring, and some of the scoring is what we call a red herring, whereas it sounds like a really great idea and it looks really cool, but it turns out it doesn't get you very many points. Other forms of scoring are very subtle, and some of them are really sneaky and turn out to really be the determinators of the game. So, try and understand it. Run through some scenarios about how your team would understand what the scoring is. Also understand what you can't do. The FRC rules always have a few things that you're not allowed to do. And so be sure you understand what those are. And run through some scoring scenarios. Play some mock games about, hey, maybe this robot is going to pick up balls and drop them in the far goal, and he'll be aligned with a couple other teammates that may or may not be able to do some things. And see if you can run through some scenarios and identify things that you feel are important and you feel are worth chasing, and conversely things that you don't want to chase. Okay. FRC games almost always have something that happens right at the end, and that something usually is worth a lot of points. So be wary of that. And some of them, last year was balancing on a bridge with Rebound Rumble. The year before that, we had you had to build a mini robot that raced up a pole. And all of these things turned out to be the determining factors in actually winning the game. Whether that's the case or not, I don't know, but keep an eye out for that end game. Okay, so that's reading and understanding the rules. So then once you understand the rules, how is it that you would like to play the game? Don't worry so much about the robot, but come up with a basic strategy. Do you want to be offensive or defensive, or a little of both? What sort of strengths do you think you can bring to the table? What do you think other teams might be likely to do? And how many points do you think you'll be able to score based on the strategy of how you'd like to play the game? Okay, and a little bit of robot design is going to spill into this. You're going to be thinking in some rough terms of what it is you want your robot to do, and that's fine. But have a plan for how it is that you intend to score. All right. Brainstorm a robot that can play your game, and so I don't know what the game pieces will be this year, but the reality is that you can do a little research online to see what other teams have done in the past. now that we're in like our 22nd year, I think, or 23rd year, when you look, you can tell, if you go back in history, you'll find that it's entirely possible that a similar game element has existed in the past. It may not be used exactly the way that you need it for this game, but it's entirely possible that the game element has existed, like is it a round thing, a square thing, an inner tube? So go back and check online, check to see what FRC teams have done in the past. YouTube is awesome. Go check out some YouTube stuff. The reality is YouTube actually works a little better because you can see how it actually worked rather than pictures and ideas that people have posted that may or may not have actually come to fruition. Because reality is important. You don't want to emulate somebody's apparently good idea and have it turn out that their good idea didn't actually work. Okay. All right. Prototyping. So you can actually learn a lot about designing robots by prototyping, and I really highly recommend that you do this. There are various forms of prototyping. Some teams will do wood and cardboard, or other teams will actually do most of their prototyping in computer-aided design, like AutoCAD Inventor or SolidWorks. And you'll come up with some basic ideas, but you're not exactly sure how to build the mechanisms. That's fine. But prototyping will help tell you whether the mechanisms you're thinking about are realistic or not. And prototypes might be just for example, last year we had to throw basketballs a great distance. Well, we all built several different prototypes trying to determine whether the ball shooters that we had in mind worked or not, right? So the other nice thing is these are rude, crude constructions, but you can evaluate the volumes of things because mechanisms take space. You can evaluate the scale of things without putting a whole lot of money or effort into it. So do use whatever materials you've got available to set out the scale, but put a little bit of time into it. Be ready for a lot of failures. Prototypes inevitably fail, and that's okay because prototyping is part of learning. Just as by way of example, if you look here's I believe this was team 2471 Mean Machine from the Vancouver area. And you can see they actually built two different prototypes out of wood. These are their early prototype machines. They came up with a couple of different ideas, and they put together a couple of robots to see if this made sense. Okay, and you can tell they put actually quite a decent amount of effort and time and effort into these. So again, it's part of the learning process, it's part of the design process, and really, honestly, this is what you do in industry. Okay. After you're done prototyping and maybe that's going to help you learn some strategies, and what you now need to do is kind of decide on what strategy you're actually going to go with, and turn some of your strategies into realities by sort of finalizing your basic design, and be prepared for revisions. Things are going to change, so don't, it's good that you're making mechanisms. Be careful about making mechanisms that are 100% integral to your robot unless you're really sure they function well. Okay, that's not so bad. Then build it. So I would spend 2, maybe 3 weeks of designing things, and take time to plan things out. And by designing things, I mean come up with some strategies, figure out how to play the game, and then do the prototyping. You may have to figure out ways of picking up things or ways of manipulating objects, right? And then spend the next 3 to 4 weeks building. And then you want to be able to divide and conquer. It's difficult to build one of these robots in a timely fashion. Doing it in a serialized format where one step leads to the other can be a little difficult sometimes on your schedule. So you'd like to have somebody, for example, working on the robot base. You'd like to have another team working on maybe putting the control system together and working with the software. If there's some sort of manipulator or ball shooter, maybe another team could work on that. And it's a good way to work together as a team. Means that you'll need to communicate, but you can handle that. All right. Some things to consider when you're building your robot. cool is cool, but reliable wins every time. And we have years of history on this. A simple, reliable robot is always better than a complex, unreliable robot. Yeah, your complex, unreliable robot may be able to score a bazillion points once or twice, but if it can't do it every time, you're probably not going to do very well. And another thing to really consider is you will be part of an alliance. And, are you a good alliance partner? What does that mean? So that means, is your robot flexible enough to do at least one or two of the tasks on the field, or did you specialize on just one? I think being able to do one or two things very reliably and well is really a good thing. Of course, if you can do everything very, very reliably, you're going to be awesome. That is really hard, and FRC games are almost always designed so that it would be extremely difficult for a single robot to be able to do extraordinarily well at each task that's provided. And hey, it's designed that way. That's how the game works. We want you to have to cooperate. So think about that when you're designing. Does this robot that we're designing seem like it's going to make a good alliance partner? And it is actually the case that sometimes doing one thing better than anyone else can be a winning strategy, especially if it's a high point thing, and especially if it's the end game. If you can do the end game really, really well every time and at least get out and play the rest of the game all right, you're likely to do extremely well. Okay, so there's some things to consider. So let's take another look at. Okay, so those are sort of the basic ideas behind the design process and how you should have a process. You should try and follow the process the best you can. Be ready to go back and redo things. Be ready to go back and revise things that may not be working out the way you intended. All right. As you can see here, here's about half dozen robots. They are all very much different. Each one of these has some unique ability that work well on the field. So how the heck do you go about designing one of these if you've never built one before? Some of these teams have been around a while, like 1318 has been around several years. Some of them, like 4205, I believe this was their rookie year, right? So, and there's all sorts of areas in between. 4077, this was also their rookie year. So there's a lot of stuff that goes into this. So let's start talking about some of the more technical stuff about where can you find resources to help you design this stuff, and what is it that you're going to build it out of, because that'll make a big difference when you go to actually design your robot. So let's take a quick look here. So there are nominally three major parts of a robot. There's the hardware, the mechanical systems, pneumatics, wheels, frames, and stuff like that. There's also electrical systems, and those are the motor controllers, the sensors, the computer, and the communications. And then there's the software. There's software control, getting feedback from sensors, and those sorts of things. And all three of these are kind of required to get a robot up and running. They overlap quite a bit. A lot of times mechanical systems have been designed that really require the electrical system to make them operate, right? And the electrical system really requires the software to do something intelligent, such as like a limit switch. Say you were raising up your robot arm. So you've built a piece of hardware that has electrical stuff connected to it, and it needs to integrate with the software so that when the arm gets to its fully extended position, the electrical system will trigger a sensor. The sensor will cause the software to turn off, right? So, these are not distinctly separate ideas. However, there are, three distinct skill sets here that need to be covered, okay? Let's talk a little bit about hardware stuff. First of all, you are going to get a kit of parts, and that kit of parts is going to have a lot of cool stuff in it. The kit of parts is designed by people who have done FIRST many, many, many times. It is there to help you get started. So if you are complete rookies to this, take advantage of your kit of parts. You normally will end up getting some sort of robot base. You're going to get all of the computer and control stuff to go with. So realize that you've got enough stuff already to build something that will roll around on the field. You just have to figure out how to assemble it. Okay. The other important thing when you're trying to figure out your mechanical systems is knowing the materials that you can use, okay? And in general, we use something called extruded aluminum. And it's aluminum that is in various shapes, okay? So starting on the left over here, you can see this is called angle aluminum, and it comes in all sorts of sizes. The secret numbers here, 6061 is a specific kind or formula of aluminum. It's kind of the standard, and that's probably 99% of what you're going to use, okay? And you can see this is angle aluminum. See, it's got a little radius down here, so it's a little stronger. That's called structural aluminum. The 6063, that material is a little softer, and it's oftentimes used more in decorative or architectural uses. And you see it has a square corner on the inside. It's still pretty strong, so don't it's a fine material, but for the most part you'll probably end up using a lot of 6061. So you can get angles. Here's channel. Channel is is a three-sided box. You can also buy plates and bars and things like that. Usually on FRC robots we sort of avoid these really big thick pieces. They weigh too much. So what you're trying to go with lightweight. So you can also find round tubing. There's 6061, and there's another one called 2024, which is a much thinner wall, but it's a different alloy of aluminum, and it's much stronger. And then there are these box shapes. These are boxed aluminum rectangles. It's called extruded. Okay, so this is probably the most common material that you're going to end up using, which is and you can get it at Online Metals. You can get actually, it turns out you can buy a lot of 6061 sort of material at Home Depot. It's a little more expensive there. And then there are a bunch of steel suppliers around, and we'll have notes for you on where to find stuff. The key one is, as far as knowing what parts are available, somebody, take your group, your mechanical design group, let them spend an hour sort of perusing the andymark.com website. This is, for all intents and purposes, the first store. And if I click on this and open it up, you can see that there's a whole bunch of really bizarre and interesting things on here. But if for example you needed to go find gearboxes or wheels, let me make this a little larger. You can go on here and you can find all sorts of drive chassis components. You can find, for some reason I can't click on wheels. Let's try that. There we go. So you can find all sorts of various styles of wheels and transmissions and electrical things. You can find gears and bearings. The prices on Andy Mark are actually not too bad. Turns out that a lot of this stuff is expensive when you're just buying one or two, because the industrial suppliers aren't interested in selling you one or two. For example, an aluminum gear like this, if you were to buy it at another place, probably cost you $50-$60. So Andy Mark does a pretty good job. They're very conscious of the fact that their customers are high school teens without a whole great deal of cash. So anyway, look around on here and just sort of get a feel for the sorts of things that you're likely to see. I think that this is a great way to learn what's available to you and what sort of things you could put on your robot. Another nice thing about this is let's pick on this simple box. This is a simple gearbox. Yeah, that's right. It's $68, but it turns out if you price the whole thing out and tried to build your own, it's worth $68. Okay, so if I click on this thing, it'll tell you what it is. And it'll tell you exactly what's coming with. There's usually some videos on how to assemble it, or I don't know exactly what this video is. Yeah, this is how to assemble it. So they give you nice video things that you can preview. You can also look under files and documents. You can find the manuals. You can find the CAD files. If you're trying to CAD things up, you'll be able to download a CAD file and incorporate right into your CAD model. Then they almost always have replacement parts over here on the side if you've broken something, or if you want to get sensors or modify what you've got going here. So I don't want to sound like a shill for Andy Mark, but the reality is that this is likely for first teams to be the store that you're going to spend most of your money on, and it really is geared towards the project that you're working on. Okay. Now that I've said that and told you all of the great things about AndyMark, there are some things that you could potentially do. They have chassis systems that you can just buy, and you know, that's fine. These actually turn out to be, you're going to get one of these anyway. A lot of teams use these for off-season sort of things, so you're already going to get one of these C-frame kits as a rookie team. Okay. But they also have drive chassis parts, so you can get replacement parts. But they also have these here we go, custom builds. That's what I was looking for. You know, a lot of teams will end up seeing you know, these really kind of cool looking robot bases. These are actually pretty expensive, and they have a whole bunch of components in them that are kind of nice. You have to be careful though. Some of this stuff will put you over the $400 price tag limit for individual parts in first. So, you know, yeah, I suppose you probably could go up here and buy a whole bunch of stuff that makes it really easy. But I think, for example, drive system parts, I'll just click on another one. If you come down here, you'll find, like, you know, big swerve drive components and these box beams. The reality is that, you know, these are really nice and really easy to use, but they are also rather expensive. So take it or leave it. But there is a lot of stuff up here. Okay, so let's go back to the slides here. So be careful about just saying, oh, well, we'll just buy everything. It sort of lessens the learning opportunities as well. Let's take a look at a couple of robots. So here's a typical robot. I think this is Team 2522. And I just wanted to show you, you know, this was from Rebound Rumble. They built a mechanism using some belting. So the idea is, you know, they drive over a ball and the ball would get sucked up these mechanisms and routed up here to their shooter. You know, it looks all really complex and stuff, but it turns out that the base here is the C base that you're going to get with your kit. So, you know, this team made good use of the materials that they were given. You can see they've got, you know, they've got angle iron. They went ahead and drilled it out to make it lighter, but that's all right. You'll be able to do that too. They have, you know, box aluminum, that rectangle aluminum. You can see some up here. You can see that they've elected to weld. You don't have to weld parts, so don't flip out if you don't know how to weld. A lot of times you can bolt them together as well. You'll come up with a way to do that. There's a lot of, you know, bearings and a whole bunch of things that maybe you have never seen before, but, you know, all of these sorts of parts you can get from AndyMark or from local suppliers. You know, so you can see there's all of the aluminum parts are sort of the mechanical system, and then there's also a bunch of electrical parts. So now if you ignore all the aluminum and realize, oh, so there's a bunch of wires going up here. Here's a motor. That motor spins this. You can see it's driven by a belt up here. And then if I follow the wires around, I can see that, you know, there's obviously a light up here that's on, and this is actually a video camera, and so there's some electrical stuff that's going on, and all of that is actually pretty straightforward to wire up, and most of it is, you know, you don't need to be able to design sophisticated electronic circuits. You just need to sort of investigate what these parts do, get help from other teams, and a lot of it is really just wiring things up correctly. Okay. So anyway, so this is a kind of a very it's a nice robot. It's got a lot of really cool stuff on it, and it's you know, it's about average on its build. I think it's actually very cleanly designed. There isn't a whole lot of extra stuff, so you know, they did actually quite a nice job on this. Let me take you to the other end. So one of our teams is very well known for doing amazing things with their milling machines and their water jets. And this is Team 2046, bare metal from Tahoma High School. And you can see that theirs looks very, very complex. But actually, when you get down here and look at it, you know, they used some box aluminum. See it up here? See the rectangles? And there's a smaller one down here. And they used some aluminum plate. And this is a piece of aluminum angle. There's another piece of rectangular, or, well, this is actually square tubing. There's some plexiglass and things. And all they've really done is smartly, they have reduced the weight by cutting away material they didn't feel that they really needed. So they wanted the rigidity of the box, but they cut away enough material to reduce the weight, and that's why they did so much work on doing all of this milling. You can see it down here. They used their CNC mill to cut all these things out. You don't have to do that, but this is just sort of like the other. This is an extreme example of a team that has the ability to do the CNC work with a milling machine, and we're able to do it. But the key is that if you'll notice, these are all this is all extruded aluminum that they put a great deal of effort into removing as much unneeded material as possible to keep their weight down. This is a beautiful robot. This is a rare robot. People don't normally put this great amount of effort into things, because this is the result of many hours on their milling machines and doing design work. Theirs is entirely done in CAD, and so the CAD program is the one that is able to cut all these parts out. Okay, so there you go. There's a couple of examples, and so again, this is all just basic materials. These are all stock parts up here. You can these are wheelchair wheels. The wheelchair wheels have hubs. Turns out that these wheels, if you go looking, you will find these wheels on AndyMark. I was just going to bring it back up, but maybe not. Oh, yep, there we go. So if I go up here to AndyMark, just to show you, there's wheels, and here are the wheels that they used. In fact, I believe these are the actual wheels that are on that robot. And then to go with these wheels, there's some hubs and sprockets and things. So so you can start identifying parts. This motor here probably came in the kit of parts. Well, in fact, I know it came in the kit of parts. This little thing here is a sensor. That sensor is actually on also available up here. If you look under actually, if I go to gearboxes and I look under the simplex, and if I come down here, I can see on the right-hand side, here's one of those sensors. You can see that there's the sensor and the wires and stuff, and that's the sort of thing that they use. It counts the number of revolutions, so it's able to tell the speed of that wheel. Okay, and again, down here, there's bearings. All of this stuff is readily available once you know where to find it. Okay, let's talk a little bit about the electrical system for your robot. These are the basic parts of the robot's electrical system. There's a battery that I didn't show, but there's a power distribution board. Or actually, this is the C-RIO controller. This is the onboard computer that drives your robot. Okay. There's this power distribution board, this big blue thing. What it does is it takes power from the battery and distributes it to all of the other things that are powered. And these black things here are circuit breakers, so it's there to keep things safe, so that you don't burn up any wires. There's this thing called a digital sidecar up here, and that is used in conjunction with the C-RIO to break things out so we can connect things to the C-RIO. These little gadgets here are called motor controllers, and then this thing is a wireless communication system. And then this is a test bench, so they actually put 2 of the motors on here. So this thing is an entire robot electrical system. You can actually turn this on, and if you use the control system, this is a slightly different version of the exact same thing. So this is the complete control system. There's the stuff that goes on the robot, and you don't have to design any of this. This is all, we give you the parts. You just need to figure out how to connect it up and wire it and make it work with the software. Okay, here's that robot control board, and this is called the classmate computer. This is called the operator's interface, and there's a couple of joysticks, or I think it might be a couple of game pads this year. These guys communicate either wirelessly or through a tether to the actual robot itself, and then the robot is able to drive these motors. So there's a great document right here. There's the link for it. Their link is also in the show notes that are on our website, and you can right now go up and look to see what last year's control system looked like. It may change a little bit this year, but the changes won't be major enough. Everything that you'll end up reading is completely applicable to this year, is my guess. Okay, so so This, all of this control stuff actually goes on to your robot. So if I go up here and look, see, I don't have a good picture of somebody's control system, but all of the sensors and so these motors connected up to motor controllers, theirs is all hidden back here, and I think theirs is also hidden down here, but you can see some of the electrical stuff popping up out here. That onboard control system is the one that's driving all the motors, is using all of the sensors to tell where things are positioned. It's using the encoders to tell how fast the wheels are spinning. Okay, so that isn't too bad. So that is sort of the flavor of what the control system is really going to be like. And if you go up and look, you can read a lot more about it online. On the software, there are three main languages that are used in FRC. There's the C++, and it's also known as Wind River, and that is a very standard programming language. It's a object-oriented procedural programming language or structured programming language, and it works great. Bazillions of people know how to program in C++. Bazillions of people do not. So it's a fine choice. LabVIEW is another fine choice. LabVIEW is put out by a company called National Instruments. They're the ones that actually built that computer that's on board. It's a very interesting programming language. It has some real nice features that are very useful, and it has some drawbacks in that sometimes it's hard to find mentors to really help you out with that. Java is another option. Java looks a lot like C++. It's considered a newer programming language. People have mixed experiences using Java with FRC. There are teams that use each of these with great success. You'll need to pick one that is going to work best for you. So if you've got a programming mentor who already knows C++, or if you have students who already know C++ very well, then that might be a good choice for you. Same with LabVIEW or same with Java. Okay. In general, all three languages, that comes with what we call default code. And the reality is that if you install the default code and you put the joysticks in position and you hook the motors up according to the instructions in the software, up to probably PW or to motor control channels 1 and 2, you put the main wheels, and if you hook it up just in a certain way, you can actually get your robot driving around without even modifying the software. And there are actually a number of teams who do very, very, very little with the software. So if you have no software expertise, we realize that as long as you guys can manage to get the computer up and running, you'll be able to get your robot driving, and then hopefully by looking at the examples or by asking other teams questions, you will be able to modify the software mildly to make it work for you. Other teams have got some students who would really like to learn how to program and would like to jump in with both feet, and I think that's awesome, and you should. It's part of the interesting part of building a robot. Okay, I highly recommend that somebody starts working on the software on day number 2. So get it set up just like they did on the on this bench, right? Or actually, I guess what we really want you to do is consider doing this. See if you can set this up, and you should start doing this immediately. Go very carefully through all of the step-by-step instructions on how to do basic wiring job on the distribution panel, a basic wiring job on the motor controllers, get your C-Rio hooked up to the sidecar, hook the motors up to the motor controllers, plug in all the control wires and a battery and the classmate, and you should be able to run these motors using these joysticks on a bench somewhere. Common mistake that I want you to avoid is putting the software off until the last week, and the usual culprit for that is your software people going, oh, that's the easy part. It's just going to work. There's no reason why we couldn't just hook it up and make it go. That is not the case. you do need to develop a little bit of experience with your software and with all of this control system stuff in order to make things work. Okay. Eventually, somebody's going to need to steal these motors and put them on the robot, and that's fine. And eventually, you'll need to sort of give up the entire control panel to the robot. But if you're able to and get the knowledge early on how to make all of this stuff wire up and run and operate, you're going to be way, way ahead of the game, especially if you're planning on using any of the more complicated sensors. Once you've got this setup going, you can try playing with the gyros or the accelerometers or the Kinect or any of the other sensors and learn how to use the sensors before you put it on the robot. It is never the case that you can write the software before the robot's done, drop it on, and expect it to work the first time. It never, ever, ever works that way. Okay, so really do that immediately. And if you can, hey, if you've got the parts or if you've got the inclination, even building a very simple secondary robot base, you know, order another C chassis or build something out of wood, you know, slap a couple wheels on it and a couple of motor controllers in that C Rio, and you'll be able to build a second control system that you can test on. Okay, really, really a great idea. All right, so I hope that this little sort of tour of what the technologies are and sort of giving you a bit more of a close-up view of what these robots look like has been helpful. I'm hoping that explaining a little bit about having a design process has been helpful, and I'm hoping that your team now has a sort of a feel of what the stuff looks like that are going to go into your robot. Things that you can do before you start, and you may remember this from last week, but I'm going to say it again. You can do a little tool shopping, and if you look up on our website, and I'll show you that link here in just a second, there's some shopping lists up there for you to look at. You can try building a robot cart that'll allow you to cut things, you know, figure out where to buy aluminum, you know, angled aluminum box or rectangular tube or round tube. You know, you'll have to try purchasing something. It's a great exercise to figure out how your school's purchasing system is going to work. And then once again, take a look at last year's rules, take a look at last year's robot documentation. You'll be way ahead of the game if you can do that before kickoff. All right, so let me show you, here's the sources of information again. So you want to, there's the first website. This will take you to, this will take you straight to the FRC section of the first website, and that's where you're going to find all of the game documentation and those sorts of things. Okay, so that's relatively straightforward. You can find, remember that under game and season info, archived game document and event results. You can click on that, and here is last year's game. Look through this. Look through the competition manual. Okay. Also, go look at the kit of parts section. There's a lot of good information in here about where to find things. You can find information about the control system, the driver station. Under electrical and motors, you can find out how the wiring is done with these wiring diagrams. And there's performance data on all of the motors here. You may or may not know what any of this stuff means, but at least you'll be able to find it. There's just a lot of really, really good stuff. Also, if you go, if you're thinking about programming in LabVIEW, which it's a fine language, you can find there's a forum up here on how to do things in LabVIEW. That's a good thing. There's also a great tutorial if you go to Robot Control System. Okay, so I clicked on Robot Control System, coming down here to the bottom. Oops, I'm sorry, going all the way up to the top. Oh, here we go. NI Control System Training Material. If you click there, you can find, these are forums. You can find some really good training material on here. And actually, what I was actually looking for was the tutorials. I apologize. Here we go. Under tutorials, You can download sample the evaluation version and go through the training materials. Okay, it's really a pretty handy thing to do. If you do hit the Start Learning Now, there's a link. There is a direct link to this up there, but this will show you in video form how to program things in LabVIEW. All right, so let's go back to other sources of information. First of all, website. The slides for this and the notes for this are actually on our website. If you go to FRC, so firstwall.org, FRC, webinars, this is Rookie Jumpstart number 2. And there are some links down here. There are links for you to go find some more pictures and a bunch of other things. Feel free to poke around in there. All right, we have used up the hour. Thank you all so much for attending, and we will keep your eye on our website. We'll be doing another one of these in probably about a week. Good day.